Good morning, everyone. It is an honor to be here today at the 7th International Conference on Welding and Non-Destructive Testing. My name is Dr. Kanak Kalita, and I'm delighted to present my keynote on how finite element simulation and machine learning can enhance the quality of friction stir welding. So, let me begin by showing the presentation outline for today. Today, I will take you through the fundamentals of friction stir welding, key process parameters, and materials. We will also explore the role of finite element analysis, followed by a discussion on machine learning meta models and their impact on optimizing welding processes. Lastly, I will present my conclusions, and I will also give some future directions. So, as we know, friction stir welding, or FSW, is a solid state joining process that generates heat through friction between rotating tool and the workpiece. The process involves plasticization in the stir zone, and there is material mixing in the thermomechanical effective zone, or the TMAZ, that we call it as TMAZ, and the forging pressure via the tool shoulder. So dynamic recrystallization in the nugget zone, in this nugget zone, ensures a defect-free joint with the superior metal properties. So there are various FSW process parameters, among which pin rotation speed, feed rate, pin pressure, and pin geometry are the most important. Now, why these are important? Because the pin rotational speed, it determines the heat input and the material plasticization, whereas the feed rate, it determines the material flow and the influence of the defect formation. The pin pressure, it will tell you about the total hole penetration and how much heat dissipation is there. Similarly, the pin geometry, it will tell you about the different kinds of shapes of the material flow, and it will also determine the joint integrity. Now, when we are talking about FSW, so when we are talking about FSW, there are different kinds of FSW materials. So we can use either aluminum on its alloys, or you can use titanium, you can use stainless steel, or you can use copper. Now, there are various types of FSW joints that we may use, or that we may need to make depending on the process or the application. So it may be some butt joints, it may be lap joints, it may be T joints, or it may be 5 joints. Now, we know that FSW finds a lot of application in aerospace, automotive, nuclear, and in various repair applications. So the objective of our work that we have done, so let me give a disclaimer here that most of the presentation that I will show here today is the outcome of a PhD work by one of my PhD candidates, he's soon to be doctor. He's about to defend his thesis. So his name is Dinesh Burande. So he has done most of the work here under my supervision. So I wanted to acknowledge him for whatever the results that you are going to see in the later slides. So our objective when we were doing this project was that we wanted to develop a high fidelity finite element model for the FSW process. We wanted to validate the finite element model through some control experiments, and we wanted to generate a process response by using some kind of design like the box banking design or Hammersley design. And then finally, we wanted to leverage the impact of machine learning to predict the weld properties of this particular welding. Now, there are various kind of platforms that are available for the finite element analysis. So we choose Abacus for this particular work. I will show some videos also to you where we have done the simulations in Abacus. So we chose Abacus primarily because it is very user friendly, and it has some advanced contact analysis properties, and it gives you kind of comprehensive analysis of features. So these were some of the reasons that we chose Abacus. Okay? But the same thing can be done in other platforms, like maybe in ANSYS also. So for this analysis, we chose the workpiece as aluminum 6061 T6 because this finds a lot of applications in the aircraft industry and in the automotive industry. So we felt that the analysis that we do would be very important for different kind of industries. Now, this is the problem description. So we are showing only a part of, given the paucity of time, we are showing only a part of the work that we have done in this particular project. So for the context of this particular presentation, so what I wanted to tell is that this is, suppose say the this is the structure that we are going to use. This is the 3D model of the FSW process. So in this, we have developed a 3D thermodynamic or thermomechanical finite element in the abacus, and we are using different kind of process parameters. Mainly, we are using the rotational speed, we are using the weld speed, and the shoulder diameter. Similarly, in the FEA workflow, we'll show you how we are setting the boundary conditions, how we are doing the setting the material properties, how we are doing the meshing, and how we are solving. And our goal while doing this, or our simulation goal while doing this, is to predict the temperature distribution as well as the residual stresses and the material flow. Now, so these are the general equations that we have used for, since it is a thermomechanical kind of analysis, so we need to also take the equations for how the heat is generated. So this is the heat generation equation. Similarly, this is the heat transfer equations that are being used in the analysis. This is the mechanical model that we are going to use in the analysis. Now, the composition of AL6061, this needs to be inputted, or this needs to be given as an input to the abacus platform. Actually, this is already present in the abacus library, so we are just selecting it from there. So next thing that we know is that since the FSW will generate a lot of heat, so most of the properties that we have, or the most of the mechanical as well as the thermal properties that we have, they are like temperature dependent. So we need to specify that at which particular temperature. For example, at the room temperature, this is the yield strength, and as the temperature progresses, the yield strength will reduce. Okay, so this is a standard kind of data that you can have for the material from the design data group. So we have to give this also as input to the program, or to the abacus program. Next, what we are doing is the first step is that we have defined the problem and we've gathered the data. Then we have created the geometrical shape that we want to analyze. It looks something like this. So here, this is the workpiece, and this is the tool that we have. Next, this is the contact. We have made the contact of the tool and the workpiece, or this is the assembly phase in the abacus. Next, once we do that, then we have to set the boundary conditions. Okay, so in the boundary conditions, we have set the different kind of boundary conditions, the thermal boundary conditions as well as the mechanical boundary conditions. So let me show you here. So these are some of the various kind of contact coefficients that we need to define. That also we have defined in the abacus. And depending on what is the direction of the movement of the tool, we have set that here in the abacus. After that, we have set here the restraints or the boundary conditions for holding the workpiece. It is like simulating that the workpiece has been held in a jaw or maybe some kind of clamp. So that we have simulated it here. And the next step is, so next we have defined the tool geometry as well as the movement of the tool. So after that, we have meshed this particular model. So we have broken, or we have discretized this particular geometry that we have into small blocks, and these blocks are known as the finite elements. Okay? So actually, we'll get the solution of this particular problem at each and every nodes of this particular elements. So once this is done, then we can now begin the simulation. And then depending on what we want to study, for example, in our case, we wanted to study the temperature generated, and as well as the heat generated, as well as the residual stress. That is what we wanted to study. So let me show you a particular video of what it looks like. So this is the video of the nodal temperature. So this is the tool is moving. As you can see, the tool is moving forward, and this is the temperature distribution that you can see across the weld line. Similarly, the same simulation when we show it for a stress generation, so you can see how the stress is generated. So as the tool moves forward, so the stresses are generated here. You can see that what is the maximum stress that is generated. Of course, we are studying here only the ศ์stress, but we can also study the stresses in the different directions here. Next, once we have done that, so what we'll do is that we wanted to kind of replace this simulation, because this simulation takes a lot of time, because most of this simulation would take, each simulation would take at least 30 to 40 minutes. So we wanted to replace it by some kind of a machine learning model. And this is something what we call as the meta model or the surrogate model. But for that, initially we need some kind of pilot data or some kind of training data to train the machine learning model. So for that, we have used a particular method called the box banking design. So using the box banking design, we have taken three different levels or three different range of this. Suppose say the three different parameters that we have. We have the parameter. So we have the n is the rotation speed. We have the feed rate, as well as we have the shoulder diameter. So depending on this, we have some total 15 combinations of experiments. So these 15 experiments we have conducted in the abacus or in the finite element, and then we have recorded the nodal temperatures and we have recorded the ศ์stress. So these are some sample images of how the distribution look like. This is a distribution of the nodal temperature. This is a distribution of the ศ์stress, and this is when we are seeing it across the cross section. Now, when we look into this particular, image, we'll see that it shows us the distribution of the temperature across the weld line. Okay, so this is, suppose say, the weld line. So this is the welding is happening in this direction. So here, this red line that you see here, so we are recording the temperature profile for this particular line. So what we have done is that we have tried various combinations. Among this, I have showed here only for 3 combinations. This combination low represents this value, that RPM is at 1000, then weld speed is as 280, and shoulder diameter is 17. So this is what it represents, the red one. Similarly, for the high level, high simply means that this is the maximum level of parameters that we have set for our experiment. So the tool rotation speed in this particular case is 1500 RPM. The welding speed is 787 mm per minute, and then the shoulder diameter is 21. So depending on this, we recorded the temperature at each and every point across this red line that you see here, and that is what we have plotted here. So negative indicates from this side and positive indicates from this side. Now, similarly, we have done the same exercise for the ศ์stress. This was for the nodal temperature, and this is for the ศ์stress. We have recorded three different combinations of the process parameters. So one distinct thing that you can see here is that all of this, in all these cases, they follow a definite pattern. We'll discuss more on this in the later slides. So the outcomes that we found out from the FEM study was that high rotation speed, when we combine with low welding speed, then there is a increase in the heat generated. Similarly, when there is a moderate rotation speed with higher welding speed, then we have some reduction in the heat generated. Similarly, the large shoulder diameters and higher rotation speed would increase the residual stresses. And we saw that the thermal analysis also revealed that the temperature distribution has a very distinct pattern, and the heat affected zone exhibits thermal behavior, more thermal behavior as compared to the rest of the joint. Okay, that is the common sense, but this is also what our common sense tells, and this is what we saw from our analysis. Now, the problem with all these simulations is that unless you validate it with some kind of experiments, that is not usually considered to be true by the scientific community. So what we have done is that we have done some physical experiments. So by doing these experiments, we saw that we recorded the temperature distribution across the well line using some thermocouples, and we saw that this is the pattern that we observed in our experiments, and we saw that the experimental verification was very near or very true to our simulations or our finite element simulations. So we have recorded it for 3 different cases, again for the low, medium, and the high cases, where at 3 different combinations of these process parameters we have recorded it here. Next, similar exercise we did for the residual stresses, and we saw that the pattern was maybe there is a deviation of 5 to 10% in the values, but we saw that the pattern that it followed or the trend it followed was definitely matching. So it means with a good amount of confidence we can say that the finite element simulation or the finite element model that we have built are very accurate, or they are very representative of the actual experience. So now what we can do is that now we can use this particular finite element data, and we can then go on to make some machine learning models. So for making the machine learning model, what we are doing is that we are following this particular structure or this particular methodology. So in this, what we have done is that we have tested and various machine learning models, like we have tested it for linear regression, we have tested for random forest, for support vector, for gradient boost, and so on. So many different kind of models we have tested and validated using this. So this is the once we have the training data. Okay, so one thing I should tell you here is that initially what you saw here, let me go back here. So we initially had 15 experiments that we derived using the box banking model. So this was initially done to mainly to study the effect of the various process parameters and to study whether our finite element are effective or they are as accurate as the actual experiments or not. Once we have done that, so before starting the machine learning phase, what we did was that we again generated some high fidelity data. What we used was that we used another method called a Hammersley design. By using the Hammersley design, we generated some 100 points, 100 new data points, and then this 100 data points were used as the training data for training all our machine learning models. And the box banking design data points that you saw earlier, we use them only as the test. Okay, so we use them as the independent test. This data points of the box banking were not given to the machine learning initially. Once we trained the entire machine learning model, after that we gave this as the test, okay, so that we could validate whether our model was accurate or not. So this is the visualization of the data that we have, and here you can see the correlation of the various parameters that we studied, or the various cases we studied. So one thing we observed here was the lack of multicollinearity as such. Next, what we did was that we predicted the temperature using machine learning for various kind of models. So each of these particular graphs represent different kind of models. We have shown only some 9 models here, but in reality we have done a lot of other models also, other machine learning models also we tried. So here I have shown for linear regression, for like grid search CV, for gradient boost, maybe for ADA boost, and so on, random forest, and so on. Some of these graphs are shown here. So in most of the cases, what you will observe is that if the data points are very close to this diagonal line, then it means your prediction is more accurate. And if the data points are far away from this diagonal line, or this unity line, or this identity line, then it means your predictions are somewhat not correct. Okay. So so as you can observe that maybe for the 𝐧𝐶-boost regressor or 𝐧𝐶B regressor, these data points are directly on the line, so it indicates that these are more accurate. Similarly, we did another analysis called the residual plot analysis. Again, from this, if you see that the data points are lot of scatter is there in the data points, so it means the model is probably not the best model. And if you see that the data points are clustered or cluttered around the around this mean line or the zero line, then the residuals are very low, and then it is representative that the particular model is more accurate. So this exercise we did for the nodal temperature. Similarly, then we recorded the various accuracy metrics. For example, we recorded the R square, coefficient of determination. We recorded the mean absolute error, and we recorded the mean square error. Similarly, we did it for the training data. It means we did it for the data that we generated using the Hammersley design, and we did it for the test data. It means we recorded it for the data that we generated using the 𝐍𝑑𝑒sign design. So once we did that, then we saw that for the XGBoost regressor, on both like the train as well as test, we are getting very high accuracy. So it means this particular model is very, very accurate. Similarly, we repeated the experiment for the 𝑍𝐵 stresses also. The last time we studied only the nodal. Now we studied the 𝑍𝐵 stresses also, and we recorded the various prediction error plots as well as the residual plots. And similarly, we recorded the R-square values, the mean absolute values, and the MSE values for both the test and the train cases. And from this, we found out the outcome that in general, what happens is that ensemble techniques such as the extreme gradient boost and the random forest, they are more robust to predictions and they have very minimal error. We also observed that the integration of machine learning with finite element accelerates the parameter process optimization, reducing dependency on physical experiments. And in future work, we plan to expand it to other materials. We plan it to expand into other welding types as well. So in conclusion, what we can say is that the process parameters that we have for FSW, they are very significant in influencing the temperature and the residual stresses in FSW. And finite element provides very accurate kind of predictions, which also reduces our need for the extensive physical experiments. But of course, you need a couple of physical experiments to validate whether your finite element is accurate or not. And then, of course, you have the machine learning models, which are data-driven and which can be used for optimizing the entire welding process parameters. We can improve both the efficiency as well as the welding quality by using it. So we believe that this particular research paves the way for advancing AI techniques in welding technology to improve the manufacturing process. So for all those who are interested in this topic, these are some of the future scopes that I feel, or we feel, that will be very good in terms of studying the effect of the various process parameters as well as the impact of AI on this. So we feel that the future scope could be, people could work on expanding the data set with real-time monitoring and control adaptive strategies, as well as people could explore like hybrid ML FEA frameworks for predictive modeling. And there could be some works which could extend the ML applications to other advanced weldings like the laser welding and ultrasonic welding. And this brings me to the end of this particular presentation. And these are some of the work that have been produced as the outcome of this particular study that I've shown here. Maybe if you like my work, you could refer some of those. And thank you once again to the IWNT and Malik Astar University, as well as the organizers of this conference, of the 7th International Conference on Welding and Non-Destructive Testing, for inviting me and giving me an opportunity to address the gathering and to give a presentation in front of you. Hope it was useful for all of you, and I hope that all of you who are working in this area will read our work, will try to do similar work or maybe advance this work. Thank you once again to everyone.